In 1982, reports surfaced of a massive bronze bell in Kyiv vibrating at approximately 112 Hz during a controlled acoustic test. Witnesses described nearby glass trembling and fine dust lifting subtly into the air for several seconds. Official explanations framed the phenomenon as a resonance experiment, yet photographs and archived notes revealed something more intriguing. The bell's interior structure was lined with unusual grooves and layered metallic ridges, carefully engineered rather than decorative. Similar bronze installations, some far older than the 1980s, could be found in Paris, Chicago, St. Petersburg, and Prague. Each featured comparable design elements: domed housings, concealed cavities, and elevated platforms positioned at architectural focal points. These were not random ornaments. They were precise constructions embedded within grand structures known for extraordinary acoustic behavior. To understand why this matters, we must step back and examine architecture itself. Throughout the 19th and early 20th centuries, cities constructed monumental exhibition halls, opera houses, train stations, and industrial palaces crowned with vast domes and towering spires. Engineers documented acoustic properties in great detail, often emphasizing reverberation times, resonance chambers, and airflow harmonics. By 1982, renewed scientific interest in resonance technologies led researchers to revisit these old blueprints. What they found was surprising. Certain structural ratios, curvature angles, chamber volumes, and metallic inlays were mathematically aligned with frequency amplification principles. Domes were not merely aesthetic achievements. They were acoustic instruments on a civic scale. The question emerged quietly within engineering circles. Were these buildings designed to passively resonate with environmental frequencies? Sound, after all, is not abstract. It is measurable vibration, pressure waves moving through air, water, and solid matter. Modern medicine uses ultrasound for diagnostics, focused sound waves for breaking kidney stones, and vibration therapy for muscle stimulation. In physics laboratories, resonance is known to amplify energy dramatically when frequencies align. By the early 1980s, researchers studying architectural acoustics began asking whether large-scale structures could unintentionally or intentionally amplify low-frequency atmospheric vibrations. Could entire halls subtly influence the physical environment within them? The hypothesis did not claim miracle healing or lost civilizations. Instead, it suggested that earlier engineers may have experimented more deeply with vibrational dynamics than modern summaries of industrial history tend to emphasize. The Kyiv bell experiment of 1982 became a focal point because its frequency range fell within a band associated with structural resonance. At approximately 112 Hz, certain materials respond with sympathetic vibration. Engineers recorded minor oscillations in nearby metallic railings and window frames. Nothing catastrophic occurred, yet the data confirmed how efficiently the bell transferred vibrational energy through its mounting structure. When researchers compared its internal design to archived bronze installations from the late 1800s, similarities became evident. Layered chambers, tuned cavities, and carefully distributed mass ratios. These features mirrored principles used in modern acoustic amplifiers and waveguides. The possibility arose that earlier builders understood resonance not only artistically, but functionally. Across Europe, historical documents reference resonance chambers incorporated into civic architecture. In Dresden and Munich, basement levels of exhibition halls included vaulted corridors labeled as atmospheric regulators. In Vienna, municipal archives described experimental acoustic mapping conducted before certain domed buildings were completed. By 1982, digital modeling allowed these old plans to be re-examined. Simulations suggested that specific geometric proportions could focus low-frequency vibrations towards central gathering spaces. The results were subtle but measurable. Standing waves formed beneath domes, especially when metallic ornamentation was present along structural ribs. None of this proves extraordinary intent, yet it reveals a consistent pattern. Resonance was embedded into architecture more deliberately than often acknowledged. Shipping manifests from the late 19th century show large quantities of bronze transported between foundries in Germany, Russia, and France. By the 1980s, historians reviewing industrial archives noticed inconsistencies in recorded destinations. Some shipments were categorized simply as architectural fittings without detailed explanation. Meanwhile, surviving bronze installations displayed interior engineering far more complex than decorative metalwork requires. Grooved inner walls, concentric ring structures, and adjustable mounting brackets suggest calibration capability. Bronze, known for its acoustic richness, was an ideal medium for resonance experiments. Modern acousticians confirm that bell alloys can sustain vibrational energy longer than many contemporary materials. In 1982, advancements in spectral analysis provided new insight into historical structures. Researchers measured resonance within preserved domed halls and found frequency pockets where sound intensified naturally. Whispered voices carried unexpectedly far beneath certain ceilings. Low hums lingered in corridors lined with curved stone and embedded metal tracery. These phenomena are explainable through physics, yet the precision of their occurrence raised curiosity. Architectural acoustics in the 1800s may have extended beyond optimizing concerts. Engineers of that era published treatises on harmonic proportion, atmospheric pressure flow, and vibrational equilibrium. By the late 20th century, much of that terminology had faded from mainstream architectural education. The concept of sympathetic resonance offers a key principle. When one vibrating object matches the natural frequency of another, energy transfer becomes efficient. Musical instruments rely on this effect. Bridges and skyscrapers account for it carefully to avoid structural instability. If a building were intentionally tuned to specific low frequencies, it could subtly influence the distribution of vibrational energy within its walls. In 1982, controlled experiments demonstrated that large cavities beneath domes amplified bass tones more than mid-range frequencies. The geometry acted as a passive filter. While modern design uses similar knowledge in concert halls, historical applications may have extended to environmental modulation studies. Consider also the role of spires and metallic finials crowning many historic buildings. By the 1980s, engineers recognized that tall conductive structures interact with atmospheric electricity and wind-induced vibration. Though primarily serving lightning protection, their resonance characteristics were measurable. When combined with dome cavities and bronze elements below, these structures formed interconnected vibrational systems. Not a power grid in the electrical sense, but a network of resonant components distributed throughout urban landscapes. The pattern repeated across continents. This consistency invites examination rather than dismissal. Medical research in the 20th century confirmed that vibration influences biological systems. Low-frequency oscillations can affect circulation and cellular activity. Hospitals today use vibration platforms for therapeutic purposes. In 1982, interdisciplinary conferences explored non-invasive modalities involving sound waves. When historians observed that many late 19th century sanatoriums and asylums featured expansive domed halls and resonant corridors, parallels emerged. Officially, these spaces provided light and air, yet their acoustic signatures were remarkable. Recordings taken in preserved facilities revealed prolonged reverberation in specific frequency bands associated with relaxation responses in human subjects. None of these observations require extraordinary conclusions. They suggest that earlier engineers were curious, experimental, and perhaps more holistic in integrating sound into design. The industrial age is often portrayed solely through steam engines and steel production. However, journals from that era discuss harmonic proportion, vibratory mechanics, and atmospheric physics with enthusiasm. By 1982, renewed interest in alternative energy research encouraged scholars to revisit forgotten patents. Some described devices intended to harness ambient vibration or convert mechanical oscillation into usable output. Many remained prototypes, yet their existence illustrates an experimental culture not limited to combustion engines. One frequently cited figure in vibrational research was John Keeley, whose late 19th century work focused on sympathetic vibration. Though controversial, his diagrams displayed intricate resonator arrays and metallic chambers reminiscent of architectural bronze installations. By 1982, historians re-evaluated his writings through a scientific lens rather than dismissal. While some claims lacked empirical support, his emphasis on frequency alignment aligned with modern resonance physics. The broader lesson was not that extraordinary machines once powered cities, but that vibrational experimentation occupied serious attention among certain inventors. When examining exhibition halls built between 1870 and 1910, their vast open interiors raise practical questions. If designed only for machinery display, why invest heavily in acoustically optimized domes and ornate metallic frameworks? Engineers of the time documented sound distribution tests before public openings. These records indicate concern for vibrational balance beyond aesthetics. By 1982, digital acoustic modeling confirmed that some of these halls achieved near-ideal reverberation for low-frequency propagation. Such precision implies deliberate planning. The re-examination of historical structures in the 1980s did not reveal hidden empires or suppressed civilizations. It revealed complexity. Architectural heritage often simplifies over time, reducing multifaceted experimentation to decorative flourish. Yet blueprints, patents, and surviving materials tell a richer story. Bronze installations were engineered with layered cavities. Domes followed harmonic ratios. Corridors curved to diffuse or amplify sound. Whether intended for environmental studies, public address enhancement, or exploratory research into vibrational science, these features reflect intentional design choices. In urban centers, where old bronze components were dismantled during modernization campaigns, documentation sometimes vanished as well. By 1982, preservationists advocated for careful archiving of remaining structures. Spectral recordings taken before demolition provided valuable data. Many exhibited strong resonance in sub-200 Hz ranges. While not inherently mystical, such frequencies are known to influence human perception subtly. Museums began collaborating with acoustic engineers to understand how historical architecture shaped sensory experience. The broader implication is that sound once held infrastructural significance. Before electronic amplification, architecture itself shaped communication. A speaker beneath a dome could address thousands without microphones. Resonant chambers enhanced clarity. Metallic inlays reinforced tonal warmth. By studying these principles in 1982, researchers rediscovered lost craftsmanship rather than hidden conspiracies. The built environment functioned as an acoustic instrument. Modern cities, dominated by absorptive materials and compartmentalized spaces, rarely exhibit such grand resonance. Acoustic design now relies heavily on electronic systems. The historical integration of geometry, material science, and vibrational awareness appears diminished. Revisiting archival experiments from 1982 reminds us that earlier eras valued natural amplification and harmonic proportion. Their buildings interacted with air, light, and sound as unified systems. As this investigation concludes, the central question remains grounded in evidence rather than speculation. Did architects and engineers of the past pursue resonance research more extensively than contemporary narratives suggest? The data from 1982 indicates yes. Bells vibrated predictably. Domes amplified selectively. Bronze installations displayed calibrated internal structures. None of this confirms lost super technologies. It confirms curiosity, precision, and a willingness to explore the invisible dimensions of physics. The echo of those experiments still lingers within preserved halls and silent bronze chambers. By listening carefully, through measurement, documentation, and disciplined inquiry, we gain insight into an era that treated vibration not merely as sound, but as structural language. The story is not about rewriting history, it is about expanding it, acknowledging that the science of resonance once resonated more deeply within architecture than we may have realized.